Chapter 3 is all about derivatives. So the first thing I want us to do is define what a derivative is. So let's go back. A reminder that a big problem in calculus is finding the slope of a tangent line to a slope on a curve. So the slope of our secant line at point A, f of A, is the rate of change in y in relation to the change in x. And we can approximate the slope of a tangent line by using this secant line right here. So for example, if m_sec equals 3, it changes 3 times as fast as x. If we choose a value of x near a and draw the line through a f of x and x f of x, we'll find the slope of a secant line using this different quotient, right? But what if we let x minus a equal h? Then we have that x equals a plus h, and we can rewrite slope as follows. This is a really common way to rewrite slope. So here's the formal definition of a difference quotient. Let a function be defined on an interval I containing a. If x doesn't equal a, is an I, then we have the following, which is a difference quotient. Also, as long as h doesn't equal 0, is chosen so that a plus h is an I, then we have q as the different quotient with an increment in h. Okay, so the tangent line, friendly reminder, is the limit of our secant line. And the slope of the tangent line at a is going to be the rate of change for the function is at a, right? So we need to keep all of these lovely things in mind as we're approaching derivatives. So here's how we would go about approximating tangent lines, right? Using our new definition where instead of x we have a plus h. And here we have our tangent line, where before m_sec was that the slope of the secant line. This is the slope of the tangent line. Here we have it defined as the limit. So why don't I go ahead and find the tangent line to x squared at x equals 3. So m tangent equals f of x minus f of 3 over x minus 3. So f of x is x squared, and if I substitute in 3, I'd get 9. So I have x squared minus 9 over x minus 3. My numerator factors. And I am left with x plus 3. I now take the limit as x goes to 3 of x plus 3, and that's going to give me 6. So this gives us our slope. Since it is tangent to the graph f of x at x equals 3, our tangent line passes through x comma f of x, right? So it's going to pass us through x comma f of x, which is 3 comma f of 3, which is 3, 9. So our line passes through this point, and it has a slope of 6. Because now we have a point and we have a slope, we can use point slope form to find the equation of our tangent line. So I have y minus y1 equals m times x minus x1. That be y minus 9 equals 6 times x minus 3. So y minus 9 equals 6x minus 18. If I add 9 to both sides, I have y equals 6x minus 9. So y equals 6x minus 9 is the equation of the tangent line to f of x equals x squared at x equals 3. Now let's find the slope of the tangent line to f of x equals 4x plus 1 at 2. So the slope of my tangent line is going to be f of x minus f of 2 over x minus 2. So that's my change in y over my change in x. So I get 4x plus 1 minus, if I substitute 2 into my function, I get 4 times 2, which is 8, plus 1 is 9, over x minus 2. That gives me 4x minus 8 over x minus 2. 4x minus 8 divided by x minus 2 is just going to be 4. So this gives me my slope. I now need to know a point on the line. So I know when x is 2, y is 9. So I have y minus 9 equals 4 times x minus 2. Again, using point slope form, I know my slope, I know a point on the line, and I can solve for the equation. So I have y equals 4x plus 1. And this is the equation to tangent to 4x plus 1 at 2. And as you can see, it's the same as our original equation. The limit is used to find a tangent line. The limit used to find a tangent line is called the derivative. The process of finding the derivative is called differentiation. So if we want to find the derivative of, so for example, f of x equals 3x squared minus 4x plus 1, we're going to find f prime of x, and f prime of x will equal the limit as x goes to 2 of f of x minus f of 2 over x minus 2. Let's go over a couple examples using velocity and instant velocity. So friendly reminder that speed equals distance traveled over rate of time traveled. So for example, that's going to be miles per hour, right? That's how we'd write that as a ratio. Suppose the function s of t gives the location of an object on the line t. We can use the ideas of secant and tangent to find average and instantaneous velocity. So now for the function s of t, the instantaneous velocity at time t equals a, we'll define that as s prime of a, or the derivative of s at a. So a homeowner sets their thermostat so that the temperature in the house begins to drop from 70 degrees at 9 p.m. and reaches a low of 60 degrees Fahrenheit during the night and rises back up to 70 degrees by 9 a.m. the next morning. Aren't we so glad we all have smart thermostats? Suppose that the temperature in the house is given by the formula T of T, right, which equals 0.4 T squared minus 4T plus 70, as long as T is between 0 and 10, right? When T is the number of hours past 9 p.m. I want to find the instantaneous rate of change for the temperature at midnight, so I'm going to have to take the derivative. So if I take T prime of the temperature at midnight, I'm not going to plug in 12. I want to know how many hours is it past 9. Well, midnight is 3 hours past 9. So I have T of 3 is the limit as T approaches 3 of big T little t minus big T of 3 over T minus 3. So this is the limit of 0.4 t squared minus 4t plus 70 minus, if I substitute in 3, I get 61.6 over t minus 3. This is going to factor. Limit of 0.4 times t minus 3, t minus 7. This t minus 3 in our denominator is going to cancel. So I'm looking for the limit as t goes to 3 of 0.4 times t minus 7, and I get a negative 1.6. So my instantaneous rate of change of temperature at midnight is negative 1.6 degrees Fahrenheit.